Welcome to this topic on engine air, and this is going to be, and it's on Airbus A320, and this is part of Powerplant. So it's going to be about 8 or 9 different topics that comprise the Powerplant concept, okay, and everything pertaining to that. So with engine air, we're going to be going over the clearance control systems. Also just understanding conceptually a little bit about engine air. What happens if we don't have air running through the engines? I've talked about this before. The plane's not going to fly. You have to have air, compressed air in particular, but going through this process, and it has to be done efficiently in order to create a certain outcome. We're talking about thrust, delivery, and just other things that the air does to for the help with the efficiency of the engines. So we'll go over the engine air systems and some of the controls there, but we're going to also talk about the clearance control systems. So this would be your low pressure turbine and high pressure turbine clearance control. Also, of course, anytime we have moving parts, we've got to have a cooling system. So we do have that here with the engine air, creating that and providing that. Okay, so just kind of as an introduction, let's go a little bit I want to break it up like this. I'm going to introduce the air idea, okay, the idea of air, and then go into the different systems, okay, that would be your clearance control systems, and then because there's two, and then there's the valve system, and then we'll talk about cooling as well. All right, so let's go ahead and get started on this. The air itself, okay, air provides a lot of different things. We're talking about compressed air and having a way to control the airflow for the applications on the aircraft. In particular, we're talking about using air for turbine clearance control and also, bleed air. We also get engine bleed air for applications in the aircraft. Also, it's involved in variable geometry, which is basically a way to enhance the efficiency of the engine. Your clearance control, like I said before, low pressure and high pressure. And then the air is also used to kind of counterbalance, if you will, the bearing forces. And then of course we have a recirculation of air. Basically the recycling of air to create venting and just having a cooling situation for some of the areas that we want to make sure we keep a certain temperature. Also, it's responsible for sump pressurization. So when you put all these things together, as far as they're running efficiently, it's ultimately going to help the engine overall just run a lot better and just be able to be reliable for the pilots. Okay, and I'm not going to go into what the air does. We got primary and secondary flow, but the diagrams can show you. But this is like class, on Powerplant 101, if you will. So obviously we do have primary airflow, the airflow that's coming in through the engine air cowl, and then from there you got a process where you got a bypass. And then you have that secondary airflow that's created that goes externally, so around the engine. Okay, so just think about two parts to the, I say two parts, but two areas where air is important, and that's going to be your engine area and also your nacelle. Now your engine area is going to be, obviously the air is going to come in the intake cowl, and then you're going to get compressed. And then it's going to be divided, because remember I said there's primary and secondary flow. There's two different airflows. You're going to have a splitter so that one airflow is going through the core and the other is going around. So those are your primary and your secondary airflows. And your FADEC is actually going to control all of this. Okay, there's no particular order to take all these different topics. But there's a little bit of logic in watching one video before another. But the FADEC is just your full authority digital engine control, And that is the main brains, if you will, in controlling the airflow that happens when it's taken in the front of the engine. Okay, so and of course we get the guide vanes and all that, but main thing, FADEC's in charge of all this going on. Okay, and controlling it. You have the bypass air that's going to go through the exit nozzle. Okay, when things are running fine. And that bypass air is the one that's creating most of the thrust. Because remember, the idea here is going to be thrust delivery. You know, we need to have that air creating, you know, going through this process into the turbines or through the, you know, turbine sections, and then obviously for combustion with, you know, when you have air mixed, you know, mixed with a fuel or combined with a fuel, you know, you want to have that combustion so that you have, you know, a thrust that is a result of all this. Okay, so primary, secondary flow. Okay, that's part, like I said, part of the engine area when we talk about two areas where air is important. And then there's the external air system, and with the external air system, you have cooling. It's your engine bleed air, right? Because it's bled off. That's going in the external part of it. So that's where the bleed air is being used for, you know, different applications. Your low and high pressure turbine clearance control. Okay, so the air is going to be utilized for that. Also for your fuel control, and also the cooling turbine shroud cooling air. Also your high pressure compressor rotor active clearance control system, and also your your engine control unit cooling. So we'll get into cooling later, but I'm just sharing with you the external air and how it's going to be utilized. And I just mentioned all these different things right now. So okay, so that's the internal air, and then you got external air system, you know, having to do with the engine. Okay, so now let's switch to something else here a little bit, and this is going to be your front and rear bearing sump pressurizing air. So you have air here, and what's happening? We've got the sumps, and we don't want to have too much pressure in the sumps, right? So we have to have a way to vent it. Okay, so we have this air that's vented by a tube that's inside the low pressure turbine shaft, okay, to get that, so to prevent overpressure. So you have that, and then the engine bleed air, just so you know where we have bleed air that's going to applications and where that's coming from. That bleed air is coming from stages 5 and 9th, okay, of the high pressure compressor. Okay, just so you know. This also helps with it. You know, we got the anti-icing system of the air intake cowl. There's that, and there's ducting there that's routing 5th stage engine bleed port to a nozzle. Okay, so there's that going on. The cooling air for stage 1 of the vanes, okay, is low pressure, because we want to cool. We got vanes and your stators. Here in particular, and you know, obviously we got the rotor blades. We got the cooling for the high pressure turbine blades. Okay, so you know, just know that these are the different areas where air is being utilized. Okay, throughout the engine. This is for cooling, you know, cooling air. The other thing too that I don't know if you may or may not have heard of, but there's a thrust balancing air system. And you know, what does this mean? Okay, we're involving the low pressure and high pressure rotors, and essentially what we're doing is kind of relieving stress on the thrust bearings. So it's kind of an internal balancing that the air is used for, because what it's doing, it's I mean, air is a force. You can't see it, but you know, air has weight to it. There's a mass to air. And so you can actually use that, and that's what we're talking about here, and this is down to physics, but is using that air kind of as a balance, you know, kind of almost like a counterbalance, if you will, to kind of relieve some of this load on the bearings. Okay. we'll get into, later we'll be talking about some of the sensors and all that with some other things, but the reason I'm bringing that up is because you're going to see some terminology or some notations, if you will, for the Airbus A320 family that you may not have seen in the Boeing, but they're noted as PS, okay, because you're talking about pressure subsystems. So PS12, PS1, PS2, etc., etc. So these are your static pressure, okay? That's what that is, your pressure systems. And so they're denoted by these, these terms, like I just said. So your fuel control system, air bleed, the air that's bled from the fan inlet is providing pressure evaluation, okay? So it's a control parameter for the ECU, okay, your electronic control unit. Okay, so let's go into the clearance control systems. This is a big part of using air to create a clearance. Now you don't want to have too much of a clearance because then you lose efficiency. So let me just be clear on this. Obviously you can't have a rotor and a stator, because the idea here is keeping a gap between the rotor and the stators. And if you don't want to have them touching, obviously, you're going to create wear, obviously, by doing that. So there has to be enough of a clearance, but not too much of a clearance. So it's a fine tuning that's going on with this entire control system. Okay, so the gap, okay, we're talking about between rotor and stator. What that's doing, it's allowing more air in the compressor, and it's allowing more gas in the turbine to flow around the airfoils. So when it's doing that, it's increasing the efficiency of the engine. Okay, so again, we can get into all the physics about how this works, which is exciting, but I know you guys just want to know where things are located, basically. So and get a general concept of what's happening. The high pressure turbine active clearance control system here is going to use stage 4 and stage 9 air. Now I'm going to be introducing like dash 5A or dash 5B on your CFM56 because that's what's used for the Airbus A320. There again, just make sure you know which variant that you're working on. There will be a little bit of differences. It's not just dash 5A or dash 5B. There are a host of variants, but I'm just sharing with you only 2 at this point. And so the high pressure turbine active clearance control system is using air from stages either 4, 5, and 9, depending on what variant, using air from there, and it's using that to either heat or cool the support structure. So remember, air can be hot or cooled, and used for whatever applications necessary. You do have that electronic control unit that's going to be monitoring the temperatures, okay, and it's going to be using the sensors that are part of the control system. So same thing with the low pressure turbine active clearance control system. That's it's doing the same thing. Now, so I mentioned there's 2 clearance control systems, high pressure and low pressure turbine, and then there's a third system involved when we talk about engine air systems, and that's your transient bleed valve system. Okay, now again, make sure you know what variant you're working on, because this may or may not apply, but I thought I would just share this with you so you at least can hear it and at least have an awareness about it. But the transient bleed valve system is there to improve the compressor stall margin, and this is mainly during the engine start, okay, or any kind of transient situation. So that's what that is there for. Okay. Okay. So, and just where's the we're going to talk about the high pressure turbine clearance control and the components that are involved. That would be a valve. Okay, and that's located on the engine core section. And depending on, for the most part, I'm just going to tell you right now, just always refer to AMM, but just know it may be around the 3 o'clock position. Okay, that's the valve we're talking about the high pressure turbine clearance control valve. That's located on the engine core section at the 3 o'clock position. Okay, it's a closed loop system, which means it's going to use that status as feedback. Okay, that position status. There's also a thermocouple. The thermocouple is located on the right-hand side of the high pressure turbine shroud support structure. Okay, so we have a thermocouple. I just introduced the valve, got a thermocouple, and then we've got two sensors. Okay, these are your linear variable differential transformer. These are your two sensors connected to the actuator. And remember, all this information is going to the electronic control unit with, that input, so that it can, that ECU can change the valve position as necessary. Okay, so it is dependent on shroud temperature. All right. Okay, and just a little on the valve. It's a butterfly style valve, excuse me. And the valves are controlling, the compressor stage air, depending which compressor, for which engine, in each engine. There's of course the two airflows. Remember I mentioned before. So the two airflows are mixed downstream. Because remember I said when the air's coming in, the air intake fan cowl into the air intake cowl is being compressed. Okay, and then there's a flow splitter, so it's creating two airflows. But down the line it's going to be mixed downstream of the valve, and then it's going to be sent to the manifold of the high pressure turbine support. Okay, and those airflows are the shroud support. Okay, the two airflows as they're mixed and sent through, you've got that, and then there's also the actuator position. There's a sensor there, so that's being sensed, and those are those signals are being sent to the ECU as well. Okay, there's also a drain port on the valve, just so you know. Okay, the the high pressure turbine clearance control system, I mentioned the two sensors earlier. Okay, so you have that. There's also a sensor that uses the bleed air. Okay, and of course that's modulated by the ECU, but it's being it uses bleed air in response to the shroud temperature, right? Because that shroud temperature is kind of a big thing there. For being able to get that information to the ECU to give a command on position. All right, and if you're working at all on the valve itself, there's a special tooling that's necessary for installing that valve. Okay, all right, so it kind of gives you an idea with that, high pressure clearance control, and then the valve, you got a thermocouple on the right side of the support structure. Okay, and you've got that, and just kind of it's important we're going to talk about sensors, or I can talk a little bit about sensor, and where is it installed. This is a TK sensor. It is measuring, again, that shroud support temperature. The valve is going to, is being, obviously the valve is, the temperature value is being read by the ECU in order to determine, again, that clearance. Okay. Now the sensors installed at typically, I'm going to just say generally at the 330 position. That's for channel B. It's at the 9 o'clock position for channel A. All right. When you get into FADEC, and if you haven't gone to that topic yet, I'll just tell you now. The ECU has two channels, A and B, and so this information is going to both those channels. All right. So the transient bleed system. Just a little on this. The transient bleed system. It's going to control the flow of air from the 9th stage, okay, of the high pressure compressor and into the cavity of the low pressure turbine. So the transient bleed valve, because it's we're moving from the high pressure compressor to the low pressure turbine. So that flow of air increases the compressor stall margin during engine changes. It's a 2-position butterfly valve, and it is normally closed. Okay, it has one actuator, the valve body as well, obviously, and has a LVDT, that's your linear variable differential transducer. Okay, because you could also stand for transformer, but here we're talking about transducer, and basically it's just a way to translate the signals essentially, so that the ECU can recognize and give command for position of the valve. Okay, the ECU is going to be using and involving the HMU. So you've got the ECU using hydraulic fuel pressure, and that's coming from the hydromechanical unit, your HMU, to control the position of the valve. Okay, so you've got different fuel pressures going on there that the ECU is using. Okay, so actuated stroke, if there's no air, the valve is in a closed position. Okay, and then obviously if there's bleed air, then the valve is open. All right, and there's pictures and diagrams you can see what the bleed valve looks like, since there are a host of different configurations of valves. Okay, and it's similar with the low pressure. That's the high pressure turbine clearance control system that I was initially talking about, and then I mentioned the transient bleed valve. And now let's look at the low pressure and see what's happening here. There's a valve for this low pressure turbine clearance control. That valve is located also on the engine core section, but it's between the 4 and the 5 o'clock positions. Okay, so where things are located is important, as you well know. So valve for the low pressure turbine clearance control system is located between the 4 and the 5 o'clock positions. Okay, on the engine core. Okay, you have the casing, of course, for the turbine, and that's it's going to be cooled obviously by air. So talking about engine air. Any kind of discharge air is going to be utilized for cooling. That's just almost all the time that's the case. It's not going to be wasted. It's going to be recycled or discharged, and then that air being used to cool things. That's what it's doing here. The clearance control system, obviously the valve is controlling it, but the FADEC system is commanding the valve. And the FADEC interfaces, by the way, with the ECU. So if I mention FADEC or I mention ECU, they're not one and the same. FADEC is, the system itself is comprises the ECU. The ECU is kind of a go-between, so it is still going to give a command to the valve for position. Okay, so in the low pressure turbine, we're talking about the shroud clearances, right? Because we're talking about the shroud clearances clearing the tips of the rotor blades that are moving. So again, that's what the relation we're talking about. The system that here is going to be involving obviously the valve. You also have an air distribution manifold. You also have 6 cooling tubes and also an air scoop. So these are the different components that make up the low pressure turbine clearance control. Okay. The valve does have an actuator just like the other one. And just to get a configuration or get an idea of design, and you can see on the picture or diagram that it's attached to a control plate that has 3 holes. So in this particular case, there's two of the holes that are used for valve actuation. Okay, so you've got one hole ports the pressure from the servo valve to one side of the actuator, and then you have the second hole that ports to the other side. So there's your 2 holes that are utilized for actuating the valve. Okay, so that's 2. Now the third hole, that one is just a drain port, and that's just to collect leakage from the actuator and direct it into the drain system that's there. You also have a sensor that's fitted at one side or one end of the valve shaft, and that's just going to supply signals, electrical signals proportional to the valve position. That's what that's for. You also have a built-in spring return system that moves the valve to a mechanical stop. And this is the way that if for some reason, and again, if you've already gone through the video for FADEC, you'll know what I'm talking about. If you haven't, it's okay, I'm just going to say it right now. The FADEC, if for some reason there's a failure of computers that are not going to, that are responsible for the movement, for the command of valves, then there's a fail-safe position that it goes into, and this is what the mechanism is. It's mechanical. It's going to be a mechanical stop of that valve. So when that happens, in this case, the valve's going to be actually open completely. Okay, so that gives you an idea with the low pressure, the valve that's used in the low pressure turbine clearance control. There's also, let's talk a little bit about compressor control. Okay, here you've got compressor control, and here you're gonna have control of the airflow. We're talking about primary airflow through the compressor that goes downstream of the booster. Okay, so you've got that variable stator vane. Those actuators are there, and they're going to be positioning those vanes and the stator vanes, because you got inlet guide vanes and your stator vanes that are going to be on a position schedule, and that's going to be commanded by the ECU. It's going to use the HMU, because it's using the fuel pressure, to get that get that so that it's commanding that the valves, and so here it's automatically scheduling the opening and also the positioning of the valves depending on the data that it's getting, on the fan speed, things like that. Okay, so variable stator vane and your variable bleed valve, those are controlled by the ECU. Okay, so a little on the variable bleed valve. Basically what's happening here, remember variable because it's the, things are not, they don't have constant engine speed. If things change, well, there goes the engine speed, either speeding up or it's slowing down. So let's say you have the situation where you have kind of a lower engine speed going on, then you're going to have the booster that's going to be providing more air than the engine. Okay, so the booster is there kind of to boost, because the engine speed is dropped down to a certain RPMs. So the booster discharge airflow is going to be there, going to the core engine and meeting the requirements there. And of course, if there's any extra air, that's just going to be bled off through the valves, through your bleed valves. Okay, so that's what you have with that. The bleed valves are just controlling that airflow from the fan and the booster to the compressor. And it's using 12 valves to do it. So when you look at the entire variable bleed valve system, there are 12 valves involved. Okay, so just think about low as an example of low engine speed is not quite meeting the requirement, to provide enough air. Then what's going to happen is the booster is going to kick in. The booster is going to be involved, to send that air to the high pressure compressor. Okay, that's the control of the compressor's air. Okay, and so with the variable bleed valve, okay, position in relation to what? Okay, obviously the operation of the compressor, and we're talking about the high pressure compressor because you have your low and your high. But the variable bleed valve position is relating to the high pressure compressor operation. And it's controlled here by obviously the setting of the vanes, okay, the stator vanes. and they're going to open when there's a low operations, and that's just to increase the booster, the mass flow, and also to be able to match that high pressure compressor requirements. Okay. And it's a graduation with the bleed valves. Obviously, if it's necessary to have it open because there's significant engine speed decreasing, then the bleed valves are going to be fully open at that point. But otherwise, there's kind of a graduation of the bleed valves opening. Again, this is all manipulated by the ECU, or I should say the FADEC, really. But then in the ECU is going to be giving the valve position. Okay. And then as far as the interrelation with other components, the variable bleed valve system is interconnected with shaft assemblies. There are 11. Don't get hung up on the 11 part. I'm just sharing with you, potentially we're talking about somewhere around that number of 11 flexible shaft assemblies. Okay, and those are in the engine struts, and those are just providing, I'm sorry, there's 11 ferrules that are there to support the assemblies. Okay, and those ferrules are installed in the engine struts, and they're there for that reason. So you have that. You got, the system obviously open, close, and modulation, because like I said, it's kind of just kind of gradually opens. And the picture gives you an idea. I mean, I shouldn't say an engine is an engine, but you got your fundamental parts here as far as engines go. And by the way, I mean, the Boeing 737 uses the CFM56. Remember, there's different variants on the engines, but that's mostly just on the locations of, somewhere, kind of the configuration and location of some of the subcomponents of the power plant itself. Okay, so that's on the valve. A little bit on the shaft assemblies. These are unshielded power core. This is the main flexible shaft assembly. It's just an unshielded power core that has a fitting, a hexagon fitting on one end and a splined end fitting on the other. There's a spring also there, and those are there. Like I said, they're supported by the ferrules that are installed in the struts. So you have those, you have those there. Okay. Also the gear motor and your stop mechanism assembly. Okay, this is on the valve, the bleed valve. There's a motor. So this is going to be just converting the fuel into shaft power, right, using gear reduction. So, and in this particular case, in this valve, you do have a motor. You also have a stop mechanism assembly here that's part of it. So anyway, just be aware of that. Okay, some of them have a cover, some of them do not. Just be aware of that. Okay. And there's the actuator assembly that goes along with the bleed valve. Okay. And this, you can look at the diagrams to kind of give you an idea of the different subcomponents or parts to the actuator assembly, but chances are you'll be just switching out the assembly. So we'll kind of be done with that. Your position sensors, you do have those. Obviously, they need to sense where the position of the valve is, and then send that information to the ECU, right? Okay. All right, so let's kind of just go a little bit, I'm going to mention some of the parts, or some of the components to the variable stator vane system. And in this case, it has two hydraulic actuators with some transducers. And then you also have actuation mechanisms and linkages. And you also have the inlet guide vanes and also obviously the variable stator vanes. So that's what makes up the variable stator vane system. Okay. All right, so gives you an idea with that. Your transducers, you've got, I'm getting too much into the detail of it, because again, if there's some problem with them, you can switch them out as a whole. But you've got 3 windings to the transducers. They're going to be obviously translating that information to the electronic control unit. Okay. All right, so where are they located? On your variable stator vane actuators, those are located on the high pressure compressor case, and those are at the 2 and the 8 o'clock positions. Okay, so test question, where are the actuators for the variable stator vanes located? Okay, those are located on the high pressure compressor case, and they're located at the 2 and the 8 o'clock position. That's definitely a test question. Okay, so it gives you an idea with transducers and where they're located. All right, and again, it's simply giving a way of translating the signals, the information. Okay, so that gives you an idea with that. We'll go ahead and talk a little bit about the cooling of this machine. I'm talking about the electronic control unit. Because it is doing quite a bit of work with being able to take inputs and then send that information out, etc. So here we want to make sure that all electronics are that we have on the aircraft are cooled, and with here we've got what's called an air scoop, and that's located on the inlet outer barrel that supplies air through a duct. That air is going, that duct goes to the ECU to cool it. So that's where that air scoop comes in. Remember I mentioned that earlier as one of the components of the cooling system. Here we're talking about how this is. So the airflow is just going to maintain a certain temperature within the ECU. Okay, so what is it doing once it enters the ECU? That air is flowing across the cooling fins of a heat sink. Okay, so what are the tolerances here? Ambient temperature, let's say the ambient temperature is less than 100 degrees, or Mach number that's greater than 0.4, then the cooling that is entering and going through across the cooling fins is good enough. Okay. The cooling requirement, you don't have to worry so much about the actual numbers here, but when there's normal operation, that air going across there is good enough to cool the ECU. Okay. All right. So and if there's some diagrams to show you show you the cooling duct and how that's connected to the ECU unit. Okay. It gives you an idea. And kind of be aware, remember I said about dash 5 and dash 5A, dash 5B as far as a variant on your engines. There may be its position, where they're located might be a little bit different as far as your air outlets or inlets, so those are the differences. And we'll have more about this in another video, but I just wanted to raise the awareness of position differences, depending on the variant of the engine. You also have ignition cables that need to be cooled. So your ignition cables can't go past a certain temperature. So with here, what are the limits? Can't go past 204 degrees Celsius in a steady state. In transient, it cannot go past 232 degrees Celsius. Okay, so those are the limits as far as temperature for the ignition cables. And of course with cooling here, ignition system cooling, the cooling air for this igniter harness is coming from the fan frame outlet. And that's near the electrical junction box. That's where that's coming from. So the booster discharge air, remember I mentioned earlier, the booster, that discharge air is being bled from the fan frame hub, and then it's going through a tube to a junction plate at the 6 o'clock. And then that air enters the circuits of the leads, okay, that go, leads through an adapter. And that's able to create that ventilation for the ignition cables. Okay, I know I mentioned in the beginning about how I said, well, there's the engine. You have a nacelle. When we talk about two areas where air is involved, and the engine having internal system, air system, and like external air system. And now we have a nacelle section. Okay, so that was the engine part. And what's important with the nacelle, we want to make sure we have air going through, because temperature is an issue. We don't want to have it too hot in here in the nacelle. So with here, there's a probe at the exit, okay, of the nacelle to measure that temperature. And so the temperature indicating here that's going on, we want to make sure that the measurement, we don't have too high a temperature with that. As far as that probe's range of measuring, it can measure as low as -55 degrees Celsius all the way up to 300 degrees Celsius. Okay, and that signal from the probe is going into the EIU, okay, the engine interface unit, and that's going to transform that information into a digital form that goes to the ECAM. Okay, so what's the max here? So 240 degrees Celsius, that's it right there. So if it reaches 240 degrees Celsius, then that ECAM is going to be flat. That value on there on the ECAM is going to be flashing in green until the temperature drops, and then it'll stop flashing. Okay, so definitely there's a problem if that reaches 240 degrees Celsius, and then I'm talking about the nacelle temperature is reaching that, and it's going even higher than 240 degrees Celsius, then troubleshooting needs to take place. There's something wrong going on there. And they just kind of show you the display on the ECAM is what I'm talking about, just indicating that temperature. Okay, all right, so that's the nacelle, and what's important there is indicating that that exit temperature, and it's doing that by the probe that is installed at that exit. And as far as the engine itself, okay, with the engine we have internal air and the external air. We talked about that. So engine air, it's extremely important, obviously, for thrust. And we want to make sure that we have a propulsion airflow that's going on. So enough air being taken in from the air intake cowl into the fan, and then of course the compressed air that's continuing to go through to the turbine or in the combustion section to mix with the fuel, and obviously create, it's a whole, again, lesson on that if you're interested in the physics part of it. But the idea here is just that air is being utilized significantly throughout this entire engine, and the importance of the control of it to be balancing the right amount and controlling all of that in order for the engine to run efficiently. That's the purpose of the air system for this entire engine, and it being controlled. Okay, so that pretty much sums that up. If you have any questions about any part of this, certainly email us. The test questions, I gave you one of them. Locations are going to be big, so that's important to know where they are. And then just that heightened awareness that there may be some differences between the Dash 5A variant of the CFM 56 and Dash 5B. Okay, and there are other variants. I'm only mentioning two, so don't think that there's only just the two involved. Depends on what MRO you're at and what airplanes that you're getting in and what exactly is installed, in those particular aircraft that you're going to be working on. So, with that said, pay attention to, if you have to rewind this video, please do, because again, location. A lot of test questions are going to be on location, and understanding what comprises certain systems. So naming some of the subcomponents, which, like for example, on the engine section, what makes up the internal air system versus the external air system. When we talk about external air system, we're talking about ECU cooling. That's not an internal air system issue. That's an external one. When we talk about thrust balancing air, that's an internal air system issue. Okay. When we talk about front and rear bearing sump pressurizing air, that's an internal air system. See what I'm saying? Those types of differences. Okay, so again, we'll look forward to having you in the other videos.